scissors, sometimes choose paper, okay? So in order to determine what's the mixing probability, right? What is like how many times out of the entire times we play the games I choose rock, how many times I choose paper, how many times I choose scissors. What we do is we assign probabilities, right? So I play rock with a probability of alpha, I play paper with probability of beta, and I play scissors with probability of? Right, 1 minus alpha minus beta, right? Because all these have to sum up to 1, right? So the same thing here, right? Alpha, beta, and 1 minus alpha minus beta. So now, in order to, so the whole game transfers now into finding alpha and beta. What are the mixing probabilities, okay? So in order to find them, what we do is we look at what is the indifference point between playing rock, paper, and scissors, okay? So what we do is say, okay, it's, if I play rock with probability alpha, I get to win with probability if the other player plays with probability beta, okay? So it's going to be alpha beta, right? That's the, or I lose in this case, right? So that's the total winnings I can get from playing strategy rock, okay? And then I equal this to, what's the total winning from winning by playing strategy paper? What is it? Beta times what?
You are looking at the row?
The other way around, yeah. So it's going to be beta times 1 minus alpha minus beta, right? Okay? And then for the last one, equal 1 minus alpha minus beta times alpha. Right? So these are, so we have two things that we don't know, alpha and beta. And then we have two equations, this and this, for example, right? So now, just by looking at this and this, we see that alpha needs to equal beta. Right? Just from these two. Alpha equals beta. Okay? So now we use this equation and we plug in alpha equals beta. So we go alpha times alpha equals alpha times 1 minus 2 alpha. Okay? So here we have alpha equals 1 minus 2 alpha. That means 3 alpha equals 1. That means alpha equals 1 over 3 equals beta, right? So that's it. The game is solved now. So we know that the mixing probability is 30%, 33%. Okay? So the best winnings I can get under the conditions of this game is if I mix among these three strategies with probability 1 over 3. Okay? And that's how we find an equilibrium in mixed strategies rather than not finding anyone in pure strategies. Questions?
Why do you assume that the probability professor played rock and the Marina played a rock is the same?
It's the same.
What if it's different?
Yeah, if it's different, you can't solve it, right?
Too hard.
So the game, this strategy is for simultaneous move games that play infinitely. So if you play it infinitely, you actually end up with the two players having the same mixing probabilities, mixing strategies. So that's why the assumption was made there, for the same probability, mixing probability of both players.
So how is this useful in game theory, or what does it illustrate? Or
so going back to making a connection with our game, when you play the game and you have to decide what strategy you're going to use at a particular occurrence of the game, you know, first of all, that you can't go on with the same strategy over and over and over again. Because you may win the first 2 times, but then the opponent is going to know that you always choose rock,
Mm-hmm.
and she's always going to choose
Mm-hmm.
paper, and you'll be defeated, right? So from the start, you know you cannot continue with the same strategy over and over again. But then the question you have is, okay, how many times should I play rock? How many times should I play scissors in order to maximize my potential winnings, right? Because again, if you just randomize between rock and paper and you never play scissors,
Yeah.
she's going to know, right?
Mm-hmm.
She's going to react to only these 2 strategies, right?
Mhm.
But if you come with a mixing strategies of the 3, and then based on this, you find out that every 3 times you play rock, and one every 3 times you play this, but you mix it up the way you want,
Mhm.
then you know that you do the best you can to maximize your
Okay, so the point of the game is to find out the optimal rotation of choices
Right.
for
so the game
each
had 2
player.
points. One,
Mhm.
for us to understand that in repeated games and simultaneous move games, playing the same strategy is not
Mhm.
a way of playing.
Mhm.
We're always going to lose.
Mhm.
And the second is to find how to randomize what we play. Okay? Two main ideas. Yes?
So can we think of the situation as there are 1,000 Martinas and 1,000 professors, 333 of them playing Caesars, 333 playing the others? We can think of
Yeah,
that.
of course. You can have, in a game, you can have as many players as you have. And, I mean, this is just like one, small example where you have 2 players playing this, child game. But in reality, you actually have companies trying to decide, for example, when to introduce the product or advertising strategies.
Mhm.
So, and you have, a lot of players in the market, and yeah, they have to move at the same time. So, yeah, so in reality, this is much more complicated. But just for the sake of showing how mixed strategy equilibrium is found and why mixed strategy equilibrium works versus pure strategy that doesn't work, then we chose this synthesized version of the game.
Thank you.